In this video, I want to talk about the standard normal distribution and z-scores. And so I want to revisit the empirical rule, and that's why I drew this picture here of the normal distribution and the empirical rule numbers, so 68, 95, 99.7. So 68% of values that are normally distributed will fall within one standard deviation from the mean. 95% of values fall within two standard deviations, and 99.7% of values fall within three. And so the empirical rule only applies when the value is exactly 1, 2, or 3 standard deviations away from the mean. That's not usually the case. So many times, we'll be looking at data values that are not at exact standard deviations. And I'll give you an example. So I'm going to use the example of height of men in the US again. Because they're normally distributed, and the average height of a man in the US is 5'9". Instead of putting 5'9", though, I'm just going to put 69 inches. It's a little bit simpler. And then I'm going to use the standard deviation of 3 inches to get the other values. And so I've got 72 inches and 75 inches and then 78 inches. And then 66, so I'm subtracting 3, 63, and then 60 inches. And so, for example, let's say there was a man who was maybe 73 inches tall, so between 72 and 75. So that falls maybe like right here. And so we could say, well, how many standard deviations is that away from the mean? Well, it looks like it's somewhere between 1 and 2. It looks like it's closer to 1 than it is to 2, but we could actually calculate the number of standard deviations away that is, and we would get a number between 1 and 2. And so we call that a z-score, or a standard score. So a standard score, also called a z-score, is just the number of standard deviations a data value is from the mean of the distribution. And we can plot these z-scores on a special normal distribution called the standard normal distribution. So before I get to the standard normal distribution, I just want to show you real quick how we could take this example of this height of 73 inches and find the z-score for that, which is again just the standard deviations above. And looking at our picture, we should expect somewhere between 1 and 2, since that's where that value looks like it falls. And so what we can do is use the z-score formula, which is right down here. And the nice thing is it's fairly simple. We're just subtracting and dividing. The x in the formula, that's just your data value. So in our example, that would be the height of 73 inches. That's the one, that's the value that we're trying to find the z-score for. So to find it, I would just do 73 inches minus the mean, and so we can go back up to the graph here. The mean male height is 69 inches, so that goes in for mean, and the standard deviation is approximately 3 inches. And so then if you if you subtract 73 minus 69 and then divide by 3, you should get 1.3 repeating, and it means a height of 73 inches is 1.3 repeating standard deviations above average. So we don't have to have values that are exactly at, 1, 2, or 3 standard deviations. We can actually calculate for any value how many standard deviations away it is from the mean. And so like I was saying previously, though, that we can actually plot these z-scores on a special normal distribution that's called a standard normal distribution. So let's take a look at that next. So on a standard normal distribution, the curve looks like any other normal distribution curve, except the mean, which is also the same as median and mode, is always 0. So we can just label this. Remember that this line stands for the mean, also the median, and also the mode. Okay, and then we have 1 standard deviation above average. We can just put a 1 there. 2 standard deviations above average, and then 3 standard deviations above. And then we can label below average as -1, so that'd be 1 standard deviation below average, -2 standard deviations below average, and then a -3 for 3 standard deviations below average. And then just a reminder, we know that 50% of the data is always less than average, and 50% is always more more. So it's symmetric about the mean with 100% of the data values falling below the curve. And so we can take an example like the heights of men in the United States, and that example height of 73 inches that I just looked at. And we can see that we couldn't plot that on this graph because we don't even see 73 on that number line, because this is a standard normal distribution where the mean is 0. So in the heights of men, for example, our mean was 69 inches. But what we do when we use the formula is we standardize that value, and we found a z-score for it, and we found that the z-score was 1.3 repeating. And so we can see that, you know, on this standard normal distribution, if I were to plot that z-score, I would just look at the number line and I would plot it about 1.3, which looks like it's right there. And so that shows us for that particular person with a height of 73 inches, they would be about there on the number line, which shows that their height is above average. So let's go ahead and do a few more examples where we compute z-scores. So I've got the formula here written down again so we can refer to it. And so in example 2, the weights of a certain dog breed are approximately normally distributed with a mean of 62 pounds and a standard deviation of 6 pounds. A dog of this breed weighs 55 pounds. What is the dog's z-score? And then, is this dog's weight unusual for this breed? And so just before you even plug it in, let's just think about this for a minute. So if the average is 62 pounds and this dog is 55, we know that this weight is below average. So we can expect a z-score. We should expect a z-score that's negative. We should get a standard deviation of, that's negative because it's below average. So that's a good thing to just think about before you do any calculations. So now I'm going to use my formula. So my data value is the 55 pounds minus the mean, which is 62, and then divided by the standard deviation, which is 6. So in the calculator, 55 minus 62, enter, and then divided by 6, or you can put parentheses around this. And so if you do that, you should get approximately negative 1.17 for a z-score. And then the follow-up question, is this dog's weight unusual for the breed? Well, remember the empirical rule says that approximately 68% of values fall between one standard deviation away from the mean. So if this is a little bit above 1, I would say that that's pretty typical. I mean, that's still within the range of normal, so I would say this is not unusual. Really anything that's more than 2 or 3 standard deviations away, that's when it starts to become a little less common. Okay, so let's look at this next one. So this one's a little bit different. It says a dog has a z-score of negative 3.2. What is the dog's weight? So now we're being asked a different question. So I'm going to write down the z-score formula. So the z-score is equal to the data value, which would be the dog's weight that we're trying to find, minus the mean, divided by the standard deviation. So the z-score is negative 3.2, so I'm just going to plug that in, equals the data value, I don't know what that is, minus the mean, 62, divided by the standard deviation of 6. And so now we just have to solve this equation. And the best way to solve it is to multiply both sides by 6, because what that does is it eliminates the 6 in the denominator on the right-hand side. So after we do that, we have to do 6 times negative 3.2. On the left, we get negative 19.2 equals x minus 62. And then I'm going to add 62 to both sides. Okay, and then I end up getting x equals 42.8 pounds. And so we should always ask ourselves, well, does that make sense? Well, if a dog is 42.8 pounds, yet the average weight for that breed is 62, that weight would be below average by, it looks like a lot. And that makes sense because 3.2 standard deviations below average, that's definitely outside. I would say that is a more unusual weight. So now I want to do one more example. And in this example, we're looking at lengths of mature trout in a local lake that are approximately normally distributed with a mean of 13.2 inches and a standard deviation of 1.8 inches. Draw and label the distribution of trout length. So I'm going to draw a normal curve. I'm going to put the mean in the middle, which is 13.2, and then I'm either going to draw tick marks, 3 on the right, 3 on the left. You can also draw full lines, vertical lines, either one will work. And then I'm going to take the 13.2 and I'm going to add 1.8 to it to get the standard deviations on the right hand side. So 13.2 plus 1.8 is 15, and then plus another 1.8 is 16.8, and then plus another 1.8 is 18.6. And then the 13.2, I'm going to subtract 1.8 and get 11.4. Subtract another 1.8 and get 9.6. Subtract another 1.8 and I'm going to get 7.8. And so all of these numbers on this x-axis, these are in inches, and these are the trout length. So for example, if a trout had a length of 15, that would be 1 standard deviation above average. And I'm going to add a -1, -2, and -3 on the top there too, so we can see what those standard deviations are. And then it says draw and label the standard normal distribution. And so really we'd have, if we try to draw the curve in the same way here, a standard normal distribution has a mean of 0, and the standard deviations are -1, -2, -3, 1, 2, and 3. So really just these numbers that I drew on the top of the curve up here. And so we want to find the z-score corresponding to a fish that is 19 inches long. And so if we think about what that would look like on our picture, 19 inches long would be about right here. It's above 18.6, and so we're going to use our z-score to find, or z-score formula to find the z-score for a fish that is 19 inches long. So we're going to take the data value, which is 19, minus the mean, which is 13.2 inches, divided by the standard deviation of 1.8. And when we do that, we get approximately 3.22 inches. Okay. And then if we look at our picture up here where I drew 19 inches, you can see that that's above 3 standard deviations. So our calculation matches up with our picture of what we would have expected. And then for part D, how long is a fish that has a z-score of -0.85? Well, you can imagine, on the standard normal curve, -0.85, that would be almost to -1. And if I move that up to the distribution of trout length, okay, I'm expecting a trout length somewhere maybe a little bit less than 11.4. So let's do a calculation using the formula and figure out how long this fish is and see if my estimate is right. So I'm going to take the formula z equals data value minus the mean divided by the standard deviation. So the z-score is -0.85. Equals the data value, which is the length of the fish, I don't know, minus the mean of 13.2 divided by the standard deviation of 1.8. And then I'm going to solve that by multiplying both sides by 1.8. Okay, and then when I do that, the 1.8's cancel on the right hand side, and then on the left hand side I get -1.53 equals x minus 13.2, and then I'm going to add 13.2 to both sides, and so that goes away on the right hand side, and so then I end up getting x equals 11.67 inches. And so if I look at my graph, that looks like a reasonable length, since my red line up here is between 11.4 and 13.2. And then part E asked us to draw a rough copy of your answers to A and B below and label the scores. And so let's go ahead and do that. All right, so what I did is I redrew the normal distribution with all of the trout lengths below on the x-axis. So I'm going to use this graph to show where a trout with a length of 11.67 would go. So 11.67 would be somewhere between 11.4 and 13.2, so it'd be about maybe right there. Okay, and then that had a z-score of negative 0.85. And if we look at on the standard normal distribution, negative 0.85 is between 0 and negative 1. It's closer to negative 1. It would be about right here. So we can see that the line placement is the same in both of these graphs. So we took our graph of trout length, which is the one on the top, and if you standardize it to the one below, you can see that a trout length of 11.67 inches, that standardizes to a z-score of negative 0.85. And so that negative 8.85, that number, it just shows us how does that length of 11.67 compare to other trout lengths. So is this above average? Is it below average? How unusual is it? And looking at this graph, I would say it's not that unusual. It's actually pretty normal. Anything that's under the bulk of the curve, this section really is what we would consider normal or typical. It's when you get really outside of the 3, I mean, I could have even drawn that box wider. It's when you get outside of that 3 standard deviation mark where we would consider this unusual.